Thursday. Okay, good. Yeah, so I'll be talking about a few questions. So first of all, let's take a look at question B. So let's x1 to xn IID from a normal with same mean and the covariance. So the mean is theta and the variance is also theta. So that theta has to be greater than 0. And then for this model, both x bar and c multiplied by s, where s is the, well, it does not state. Okay, so then we will not make the statement as well. Then just c multiplied by s, our unbiased estimator of theta. And then we also have the formulation for c. Show that for any alpha, the estimator alpha x bar plus 1 minus alpha cs is also unbiased estimator for theta. And then for what value of alpha this estimator achieved the minimum variance. So there are two parts. One is to show that it's unbiased and then find alpha such that it has the minimum variance. Okay, so yeah, let's start from part B. Okay, so first of all, we need to show that this is an unbiased estimator. So we need to calculate the expected value for this formula, which is alpha multiplied by x bar plus 1 minus alpha c multiplied by s. And then we want to check whether this is equal to theta or not. So this is our goal. They want to evaluate the left-hand side and see if it's equal to the right-hand side. Okay, so yeah. First of all, let's decompose the left-hand side. We have a constant multiplied by the expectation of x bar, because the expectation only affecting the random variable, which is the sum of x over n. And then we also have another constant, 1 minus alpha, multiplied by the expected value of c multiplied by s. Okay. So back to the question, we know that the x bar and the cs, c multiplied by s, they are all unbiased estimator for theta. So we know that the expected value for x bar is going to be theta. So we can write alpha multiplied by theta, and then 1 minus alpha multiplied by the expected value of c multiplied by s. And this is also an unbiased estimator. So it's also going to be theta, and then it should equal to theta. So we know that this is an unbiased estimator for theta. So we have shown that it is going to be equal to the theta. Okay, then for the second part, we need to find the variance, or let's write down. So find alpha such that we have the minimum variance of that particular form. Okay, so in that case, we need to calculate the variance of alpha x bar plus 1 minus alpha c multiplied by s. Okay, so here we need to also bring the constant term outside, and then also decompose this variance of a sum. So bring the constant outside, we have alpha squared, and then we have the variance of x bar. And then we also have 1 minus alpha, taking the square, and then the variance of c multiplied by s. And then we also have a covariance term, but because they are independent, so that we have the covariance equal to 0, so plus a 0 here. Okay, so now we just need to evaluate the variance of x bar and then the variance of c multiplied by s. Okay, so the variance of x bar, where I think for this one you have, so I think you have already seen this many times, but just a brief notes that you have 1 over n squares and then sum of the variance of xi. So in that case, this will reduce to sigma square over n. And then in our case, sigma square is just theta square over n. So that's the reason why I have variance of x bar is equal to that. And then plus 1 minus alpha square, and then variance of cs. For that, we are going to use the expected value of c multiplied by s, the second moment, plus the square of the first moment. So inside the square bracket, we're just rewriting the variance of c multiplied by s in terms of a second moment plus the square of the first moment. And let's further simplify that. Okay, so the expected of okay, then there are a few ways you can address this, but maybe here you can bring the square to both c and s. So you have a c square and then s square, and you can consider the c as a constant here. That's not involving any randomness, so that you can bring the c square outside, and then you have the expected of s square. And then the first moment, which is similar as our first part, because this is an unbiased estimator, so you can write it. So expected cs is equal to theta, and then taking the power of 2, and then you have that. Yeah, I'm thinking if there's a better way to address the expected of s square. Yes, but I'm thinking it is theta square, but I'm just thinking a way to address why is theta square. Oh, it's in the handout. Okay. Yes, it is equal to theta. I'm just thinking a way to formally claim that's theta square. But if it is given, then so how do you define S here? Summation of Si square over n or n minus 1? Because that's also when I was reading this question, it does not say anything about S. So yeah, just in your handout, how is this S? Is this how S is defined? Xi square over n. Over n minus 1 or n? Okay. Then maybe I will not comment too much on this. Then I will just, so this is equal to the theta square. This is given, sigma square is given in the handout, right? Yeah. Okay. Then, yes, so I just want to say there's a lot you can comment on this one. But since it's given in the handout, then maybe I'll just use it as a given at this point. But just to make sure that you are understand or y is equal to theta. Okay, and there's also a sign that I'm yeah. So there's a second moment minus the square of the first moment. Yeah, so it's a minus sign. Theta squared. Okay. So I think the only tricky part is this one, to claim that s squared is equal to that. But yes, given in the handout, then I'll just use it as a given for the moment. But it's good to think about it. Why is that? Okay, so after we have that, we have a formulation involving alpha and the parameter theta. So now our goal is to find alpha such that we achieve the minimum variance. Okay, in this case, we are going to take the derivative with respect to alpha for this variance term. And then we should have 2 alpha multiplied by theta squared over n, then plus 2, 1 minus alpha, and then don't forget a minus 1 for the minus sign here, and then c squared theta squared minus a theta squared. And then for the rest, it's just the simplification. So this is minus 2 c squared theta squared, and then plus 2 alpha c squared theta squared minus theta squared. And then you can also group 2 alpha together, theta squared over n plus c squared theta squared minus theta squared minus 2 c theta squared. Okay. Yeah, and then all you need to do is just set that equal to 0 and then solve for alpha. And then you should have a formulation on your right hand side. And that should be the value alpha such that achieving the minimum. And then if you want, you can calculate the second derivative and then to see that's a maximum or minimum and to claim that such value of alpha achieve the minimum for variance. But yeah. Okay, so any question or comments? Okay, next we can talk about part C. So x1 to xn IID follow gamma alpha beta. Find an unbiased estimator of 1 over beta. Yeah, so so we need to design a particular estimator, and then because we want that it's the estimator for 1 over beta, so we need to make sure that the expected value of the unbiased of this constructed estimator is equal to 1 over beta. And then here we also have a hint on how to construct such an estimator. So we find the expected of 1 over x bar. So this is not x, this is x bar. And then adjust it to unbiased estimator for 1 over beta. So we first start from that, and then we'll need to perform some kind of a transformation, and then the expected value for that will be 1 over beta. But this unbiased this estimator should be constructed or by design. So we need to find the form of that, and then to make sure that a particular transformation of that is equal to 1 over beta. Okay, so now let's talk about part C. So first of all, summation of xi. I think this you have also seen multiple times. This is equal to n multiply alpha beta, where xi is following a gamma distribution alpha beta. So I think we have shown this multiple times for using homogeneous function. Now we find the expected value of 1 over x bar. This should be the x bar raised to the power, maybe you can use n over summation xi. Bring the constant outside, we have the expected of summation of xi raised to the power of -1. And this thing is a gamma distribution, so we can use the formula for e of xk, where k is equal to -1 in this case. So n multiplied by e of x raised to the power of k, and this should be a gamma function of the alpha, and then the alpha in this case is n multiplied by alpha, so n alpha plus k, and then k is -1, so minus a 1, and then beta raised to the power of k, so k is -1, and then over a gamma function of alpha, so it should be a gamma function of n multiplied by alpha. Okay, so here we have a copy of n in the front, also a copy of 1 over beta. So yeah, this is what we want to achieve. So we already see a copy of 1 over beta here. And then we have gamma function of n alpha minus a 1, and then a n alpha minus 1 multiplied by that. This is just a formula to reduce one copy of the denominator, and then you will see that the numerator and this denominator cancel out. We will have n over n alpha minus 1 multiplied by 1 over beta. Yeah, so we need to construct an estimator such that the expected value is only equal to 1 over beta. So that means we can multiply the inverse of this constant or this fraction in the front of this estimator, such that the expected value of that will be equal to 1 over beta only. So that the unbiased estimator should be in the form of a n alpha minus 1 over n multiplied by 1 over x bar. So this should be your constructed estimator. And then if you evaluate this estimator, taking the expected value, you will get 1 over beta, which is the unbiased estimator for 1 over beta. So you need to design in a way like that. Let's see, n over minus that, okay. Yeah, so any question or comments? So the answer to this question is that this will be your estimator, and this estimator is unbiased for evaluating 1 over beta. Okay, next let's take a look at part D. So yeah, I think you can read the question on your own for this part. For part D, we just need to use so D and E are related, but for part D, we just need to focusing on this part first, and then part E is more related to the details here. So first of all, let's x1 to xn be IID Bernoulli, and then it's given that the MLE for beta p square, it's theta hat of that. So this is the estimator for p square, and we want to show that this estimator is not unbiased for p square. So we just need to take the expected value for that and then see it is not going to be p square. And then we can show that it's not unbiased. Okay, this is for part D. Let me see. So, okay, summation xi over n. So, theta hat, it's summation xi over n, and then altogether square. This is 1 over n square summation xi, taking the square. And this is and then we are going to expand the summation to evaluate the square, which will be 1 over n square. And then you will have x1 square plus all the way to xn square. And then you also have the interaction term. So 2x1 x2 plus all the way to 2 xn minus 1 to xn. So the question, so you need to realize there are n choose 2 copies of different interactions between I and j. xi, xj. There are n choose 2 copies of that in this one. There are n copy of the square term. Okay, then we will have, and then I think we are ready to evaluate the expected value. And then we want to compare to p square. Okay, so E of theta hat is just 1 over n square multiplied by E of x1 x1 square, so expected of the x1 square plus the expected of the second moment plus okay, so here I'm just going to simplify in the way that is 2 multiplied by n choose 2 p square. The reason is that we have xi and xj, and then they are IID, so we have the expected of xi multiplied by the expected xj, and this is p square. So for any arbitrary xi and xj, the expected of the product is p square, and then because they are IID, so maybe I'll just put it here, IID, so that you have n choose 2 copy, and then each of them is equal to p square. So that's why we can write it in here. And then similarly, which is also the same for that, because they are all identically distributed. So we have n copy of second moment, and then the second moment is equal to the variance p multiplied by 1 minus p plus the first moment square. So maybe I'll use square bracket here. So this is to evaluate E of xi squared. So the second moment is equal to the variance, the variance plus the square of the first moment, which is p1 minus p plus p squared. And then because they are identically distributed, so that you can multiply a copy of n in the front, which is also the same idea for here. 2 times n choose 2, and then each of them is p squared. Okay, and next we just need to simplify that. So 1 over n squared maybe I can jump, yeah, you can simplify on your own, but I'm just going to jump a few steps, but you'll get the same answer. So 1 over n, p minus p squared plus p squared. Okay, p minus p squared plus p squared. And then the n copy cancel out. Okay. And then 1 over n squared multiply a 2 multiply a n factorial 2 factorial n minus 2 factorial multiplied by p squared. Okay, so n choose 2. Yes, okay. And this is 1 over n multiplied by p plus 1 over n squared. And then this 2 and the 2 factorial cancel out. And then we have a copy of n, and then a n minus 1. And the rest of the n minus 2 factorial cancel out with that, so we have a p squared. That should cancel out, and then we should have 1 over n p plus 1 over n and n minus 1 p squared. Okay, so I don't think you can further simplify that, but you can see that this is not equal to p squared. So theta hat is not unbiased estimator of what was the question? P squared. Yeah, it's not an unbiased estimator of p squared, because when we evaluate the expected of that not equal to p squared. Yeah.
What is p squared?
P is the parameter of the Bernoulli distribution P. Yeah. And can you elaborate on why is p squared? Your question regarding like why do we interested in p squared, or what do you mean by why is p squared, or what is p squared? In practice, people may be interested in any statistics. So maybe in this context, p squared is the statistic of interest. So for example, the p squared, a researcher is interested in a particular problem, and then that problem involving p squared, so that a researcher will need to find some properties of the p squared. It would depend on the problem. But in this case, without any context, so maybe it's not too meaningful. But it just people come up with different form of statistic. In this case, maybe one researcher is interested in the form of a p squared, and then they need to derive some properties of p squared, and then they want to find out the estimator for that. Yeah. So p is the population parameter. We don't know. We never know. But this person claimed that, or we say that, or someone think that this theta squared formulated in this way that can be calculated from the data xi. So if you are able to calculate this from the data, then you can know something about the p squared. That would be the underlying reason. But in terms of why is p squared, or what is p squared here, it depends on the question. Yeah. Does that answer your question? Yeah. But without any context, the formula p squared does not have any meaning here. Yeah. So we don't know what is p squared here. Yeah, but it depends on the problem. Yeah. Okay, so we see that this is not unbiased for p squared. So now we can refer back to these details here. So one way to reduce the bias, let me highlight it here. One way to reduce bias is that we can calculate theta I, where theta hat is calculated by using n-1 observations, but with xi removed from the sample. And then this new estimator given in this theta star formulated in this way. And then they want to use this estimator. And then our goal is to see that whether this theta star is able to, the expected value of theta star is equal to p squared. And then we want to see if we are able to reduce the bias entirely. So here, maybe someone else proposed another estimator called theta hat star. And then they want to see whether this is equal to p squared. So for example, the first person or the first researcher proposed this particular estimator. But this estimator is not unbiased, as we have shown here. And let's say a second researcher proposed a theta star as the unbiased, as an estimator to evaluate this p squared. And let's see whether we are able to achieve p squared. So that would be the problem statement here. Okay, so theta let's work on theta hat I, which is, so we are going to use so 1 to n, but maybe I'll use j. Okay, so j equal to 1 to n, but not, so this is the set operation, so not involving the I. And then for xi, if you don't, if you want to be rigorous, then you can write it in that way, but up to you. And then over n-1. So here I'm just repeating, I'm just using a mathematical formulation to refer that this one. You calculate the estimator by using n-1 by removing the ith sample. So that xi is removed. Yeah. So previously it was summation of xi over n. But here we are using the summation of xi by removing the I and then divided by n-1. This is referring to that. And then theta star is equal to theta hat for using all n observation to evaluate that. And then plus. Okay, so there's a n in the front. But this theta hat is also using n observations. And then n-1 over n, summation. And this I is from 1 to n, and then theta hat I. So that means you need to perform n+1 operation in total. So 1 for this one and then n for this one. So you need to calculate n+1. You need to perform n+1 operations in terms of I'm talking about computers operations, and then to achieve this, and then that would be one way to reduce bias. So okay, maybe I just not mention too much to, yeah. Okay. So here we just estimate the expected value for theta hat superscript I. And this is just one, same as the previous one here, except that it's not n squared, it's just n minus 1 squared. So we have n minus 1 squared, and then n minus 1 copy of p1 minus p plus p squared. So each of them involving n minus 1 observations. So we have n minus 1 observations multiplied by the variance plus the square of this first moment. And then we also have 2 of n minus 1 choose 2 for p squared, because theta I involving n minus 1 observations now. And then this should further simplify to 1 over n minus 1 p1 minus p plus p squared plus 1 over n minus 1 squared multiplied by 2 multiplied by n minus 1 factorial 2 factorial n minus 3 factorial p squared. Okay, then the rest is just further simplification. Let's see, p minus p squared plus p squared. And then here maybe I'm just going to jump a few steps because it's the similar in the first part. Yeah, so the n minus 1 here cancel out with 1 copy of n minus 1 here, and the 2 cancel out with 2 factorial. So we have 1 copy of n minus 1 and then another copy of n minus 2 from the numerator multiplied by p squared. Oh, okay, and then the n minus 1 also cancel out, so then maybe just simplify to 1 over n minus 1 p plus the things cancel out, so n minus 2 p squared. Okay, so that is the expected value for one of the theta hat superscript I. But what we are interested in is the theta star. So now we evaluate the expected value of theta star, which is the expected value of n multiplied by theta hat plus n minus 1 over n. Summation 1 to n theta hat superscript I, closing that. Yeah, so now we just need to plug everything into this formulation. So first of all, n multiplied by the expected value of theta hat. And this theta hat we already evaluated, which is this one here. So later we are just going to plug in the part, this theta hat that we get from the previous derivation, plus another constant term, n minus 1 over n. And again, here, because let me find a good way to talk about that. So again, it's just due to the IID, so maybe I'll just put IID here. So you can see that lots of this assumption makes to ease our computation here. So this is the fraction in the front, and the IID, so each of them follow the same distribution, so we have n copy of that, and then the expected value for theta hat superscript I. So we need to bring this part to here, and the previous part to the theta hat. Okay, so now just bring in all the components. This is equal to n multiply from your solution from the previous derivation. So which is here, 1 over n p squared. Okay, so let me just further group things from our previous solution. So 1 over n p plus np squared minus p squared. Okay, so maybe let's see if that will help us. Okay, so here I'm just bringing the first part here. So we have 1 over n. Let me just copy paste. P plus np squared minus p squared. Okay, minus a p squared. So here I'm just bringing this component. So n is in the front, and then this is in the front, plus n minus 1. So this n and this n cancel out, and then bring in the expected value here. So 1 over n minus 1 p plus, okay, so I need a bracket here, n minus 2 p squared. Okay, so the rest is just simplification. You can do anything you want and then to simplify that. So let's give it let's try it. Okay, so p plus np squared minus p squared. N minus 1 cancel out of that, so plus p, this 2 cancel out, plus did I miss something here? Did anyone see if I missed anything here? Yes. Which one? This line?
Yeah, this line.
Uh-huh.
Second part is like 1 over n minus 1 squared.
You mean the denominator?
Yes.
So up to this point is good. So okay, so you say this should be okay. One copy of that. One copy of yes. There should be a square, right? Like that.
Yeah.
Okay. Because I haven't canceled out with the numerator here. Okay. With that. Let me think about it. So this cancel out of that, so you have this and this. 2 cancel out of that, okay. So that should be n minus 1 squared, right? Yeah. Thanks, thank you. No wonder the fraction doesn't match up in the end. So here it should be n minus 1.
Yes.
Okay, good. Thank you. Nice. So that means this should be n minus 1. Yes. Okay. Okay, now it match. Okay, yeah, good. So then the n minus 1 cancel out with that, so you should have a p, and then this n minus 1 cancel out with that, so n minus 2p squared. Nice, nice. Okay, so we have 2 multiplied by p. So let me just, so that I can make sure I'm not, plus np squared, cancel out, minus p squared, removing that, plus np squared, minus 2p squared. Okay, let's group things together. Hey? Did I mess up something again? P plus np squared minus p squared. P plus np squared minus p squared plus p plus n minus 2 squared. I feel like I messed up something again. P1 minus p plus p squared. N minus 2. So one over n minus 1 p minus p squared plus p squared plus n minus 2 p squared. That's that. So this should be okay. Oh, okay, so let me double check. Maybe I copied down the wrong formula. N theta hat n minus 1. P squared minus a p squared plus a p plus n minus 1 . Okay, I must have some typo here. Okay, so I'll just make some notes. So double check the derivation here. The idea is the same. You need to plug in the formulation here, calculate the expected value to get the expected of theta star, and that should be equal to p squared. So the answer is that you remove the bias. completely. So that you can see that when someone proposing this estimator, it is not an unbiased estimator, but using this particular method, but it requires more computation, and then you are able to reduce the bias entirely. Okay, so that would be the overall idea for D&E. This one is not unbiased, but using this procedure, you are able to reduce the bias completely. So that would be the idea. Okay, I'll stop here.